For those of you who got here late, my goal today is to lay out some things that happened during a recent project that I've been working on, and then use these as sort of fodder points for hopefully some interesting ideas and then hopefully some discussion. So I'm going to try and go quickly um, through this, and then towards the end we'll break out into breakout rooms, and then you can discuss. Obviously, I mean, I won't be there. Discuss whatever you want, but hopefully something related to what we're talking about, and then we'll come back together and do that again, time permitting. So I will try and go through this. So what I'm gonna, I mean, the title. I should probably mention the title. I sounds sort of like a kind of a cheap spy novel, Code, Plots, and Values, which I chose that because that kind of made me a little bit happy. However, if any of you are in fact writing a cheap spy novel and would like to use the title, please talk to me after, and we can work out some sort of arrangement. But this actually covers pretty well what we're going to be talking about today, because I have a project having to do with values. And I ran into sort of like two issues with my code and then with the plots that I use. So we're going to dive into that. So I'll give a brief overview of the project so you get a sense for what's going on, and then I'll kind of take you into the issues, and then hopefully something good, right, comes out the other side. So values, it's a term that it's bandied about all over the place. As somebody who studies values, often used in a very sloppy way, I think. But you hear about them in, organizations over here. Organizations are supposed to have, values and value statements. We hear about them in politics. And it turns out people have been studying values for a long time. Among those who study them academically, they've settled on a couple of sort of key features. Values are abstract ideals, things like freedom, helpfulness. And they are, by definition, since they're ideals, they're desirable, right? They're things that people want, and they're supposed to function as guiding principles in people's lives. Now, sometimes these are guiding principles by way of justification, but also as truly motivational principles that can and do guide people's behavior. So I won't go down the rabbit hole of all sorts of stuff about values, but just to make it a bit more concrete, this admittedly slightly blurry picture is actually taken from one of the sort of classic pieces in work on values. And so each of these points are particular values, right? So up here we have authority, wealth, social power, and they've been grouped together into motivationally similar types, right? So distance on this plot represents similarity in meaning, or in sort of underlying motivations. And so this division into these 10 different value types is extremely common in values research, right? And so you have, for instance, authority, wealth, and social power. They're not the same thing, but all of them express this this valuation, right? This some sort of emphasis on the importance of power in different forms. And so my question coming into this project was, what explains variation in these values, right? So most people value all of these things to some degree. I've yet to meet somebody who's just like, you know what, I don't care about security at all, right? We all care about it at least a little bit. But how much we care about these things and what we do when, for instance, our desire for power comes into conflict with our desire to be like a good person who thinks of others, that varies, right, across people. And so I wanted to understand this variation. So that led me to sort of my initial idea. This is what I call sort of my early naive days as I was approaching this problem. And here was my basic idea. I said, look, values develop based on the experiences that people have. People have different experiences based on their social location, right? These, unique set of characteristics that kind of define how we're seen in society. Hence, oops. Hence, the experience in a society of being a woman is not that of being a man. It means something different, and so they experience life a little bit differently. The experience of being rich is not the same as the experience of being poor. For instance, no, just Sorry, Rohan, I wanted to throw that out there. I'm sure Rohan has plenty of financial resources, so we won't worry about that. But this was the basic idea, and it led me to do research like this. And so the details here aren't really important. What matters is that I'm taking these demographic variables, which sort of index these socially meaningful divisions, and I'm seeing how they relate to these 10 different value types, right? So we have conformity, tradition, benevolence, and the point here is that there are meaningful differences that seem to emerge among people based on their social location. Now, this seemed all well and good, and I was pretty happy with this. However, it turns out that other people did this and they got different answers. And so this is where my collaborator on this project, Catherine Ye, came in. And we started sitting there and saying, well, why are people getting different answers, right? I mean, they weren't completely different, right? But there was enough variation that we said, what's going on? At first, we thought it might be methodological, right? Maybe we've coded things differently. So if we really get the coding right, then we'll see more similarity. And we went through this long process that I would bore you if I told you, but it was, as research projects go, this long process, and we eventually ended up at this, which I think is sort of fun because this isn't even my theory, right? Like, we didn't come up with this. We found it later on down the road, actually, after we submitted this thing and got it rejected. They said, hey, you should look at this guy's paper. So this is actually a theory from a guy named Shalom Schwartz. He's actually the same guy who's sort of one of the grand godfathers of that values typology that I showed you earlier. And so this is what we ended up with. So here's what it means in terms of our question about where values come from. We had largely been looking, or for my little intuition about differences in social location was really looking at this level of the theory, right? And so the idea here is there are different institutions in a given society, say whether or not you have a job, what kind of job you have, education, and so on. And these shape the experiences that you have, and through those experiences, they shape your values. I mean, by way of example, I don't know if I need to give an example, but I mean, imagine well, actually, that was an example I actually need to give in a minute, so forget I said that. What we were missing was this part up here, right, highlighted in yellow. And what this is saying, in essence, is different places, different societies have different national cultures or different sort of like collective cultures. And those can be shaped by a lot of things, right? Like the particular history, geography, et cetera, et cetera. But the point is, at any given time, what it means, for instance, to be a German is not the same thing as what it means to be an Australian. It's not the same thing as what it means to be a Canadian, right? And these cultures can be more or less similar, but there are differences. And these differences in culture then trickle down into these institutions and shape what it means, for instance, in a particular society to be an ethnic minority, to be a woman, to be whatever the case may be. Now for that example, right, you can imagine in terms of education, look across history or across nations. Do all schools teach the same things? I mean, there are some things that tend to get taught in all places, mathematics, etc. But there's also often sort of a, what does it mean to be a good citizen? What does it mean to be a good person that gets taught? And that has changed, right, over time, and that differs across places. So an implication of this, and the thing that really kind of caught my attention, was the fact that not only should we expect social locations to predict people's values, which is what I showed you on the last slide, but we should expect that those relationships should differ or might differ across different societies, right? So again, what it means to be in a particular social location won't necessarily mean the same thing and won't have the same effect on values across different countries. So we wanted to test this. So here's what we did. We grabbed data from the European Social Survey, which conveniently included measures of values as well as a number of demographic variables that we could use as sort of to index these social locations. And we fit a model that looks like this. This is just a random a multi-level model with a random slope. So our outcome here is, one of our value types, conformity, tradition, or what have you. All of these X variables are our demographic predictors, our different social locations. And then we include a random slope for a demographic predictor so that we can see whether whether the effect varies across nations. Now, in order, and the whole crux, right, of our argument is that if we find significant variation across nations, that suggests that the effect differs, right, across these nations. So in order to figure out whether or not we actually have, significant variation, we decided to compare it to a model that was identical, except that it just didn't have the random slope. Now, to make these comparisons, right, there are lots of ways to compare models. We tried to use the most conservative thing we could think of. We looked at differences in the Bayesian information criteria, in large part because this tends to be a very conservative measure. It really likes simple models. And so we thought this would stack the deck in favor of the simple model so that if we did find variation, we could, feel more confident about it. Now, we had to pick some sort of cutoff point. So based on the literature we've read, kind of the rule of thumb that's out there is differences of about 2 are considered to be evidence or sufficient evidence that one model fits better than another. They'll keep that in mind, right? Because this is actually something that somebody who I'm assuming was not familiar with that literature, a reviewer asked me about, right? Like, why are you doing this? And this is something I'll pick your brain about a little bit later. But this is what we did, right? So if this model fits better by at least 2 of these BIC units, we said it looks like there's variation on this trait, or on variation in this particular relationship, right, between demographic position and values. So this is where things start to get complicated, right? Because it seems like a pretty straightforward analysis. However, step 1, we have 10 different values. And in the ESS, we have 12 of these social location variables. So that gives us 120 multi-level models that we need to fit, plus 10 of our comparison models, the models without the random slopes. So 130 multi-level models. It's kind of a lot of models, but we can manage that, right? But then I got thinking. I said, Andrew, you believe in doing good science, right? And it turns out that you don't just have one wave of data here, right? The European Social Survey actually comes with 8 different waves. And so I settled on this idea, which I still am absolutely thrilled with, right? Of running my analysis and then replicating it in all 8 samples, right? And this is for like a social scientist, particularly somebody who's having to use cross-national data. This is like a dream, right? I can do an exact replication in 8 independent samples, which is awesome, right? Like this is a great way of sort of establishing what's going on. However, it does mean instead of fitting 130 multi-level models, I'm now fitting just over 1,000 multi-level models. And to make things even more exciting, there are, of course, missing data, and I don't want to be a chump. So I'm like, I got to handle this missing data. So I do multiple imputation. I decided to do about 30 imputations, which then puts me in a situation like this. I now have to fit those models in each of my 30 imputed data sets. And let me see if I have in my notes here the overall total. I think this gives me somewhere just above 31,000 models to fit. So I say, hey, well, that's a lot of models. But this is a great coding challenge. I'll jump in there. And I had a lot of fun in R coding this up and trying to estimate all of this. And there, you know how coding goes, right? There are all sorts of, twists and turns and deal with this problem and whatever else. But it was enjoyable, right? Now, this is where we run into our first problem. Problem number 1, memory. So R, by default, right, it holds all of your data in the actual working memory of your computer. Now, 31,000 models. Each of these models, when I checked, they were about 25 megabytes. Now, again, I'm not like a computer science person, but I think that's somewhere around 780 gigabytes. And I don't have that much RAM on my computer. right? And so this was a challenge. Like I'm like, how do I do this? So what I decided to do, instead of going through and actually storing the original models, which is what I wanted to do, right? Just in case I needed to go back and look at something, I'm like, I can't store 31,000 models. So what I'll do is I'll create a function that runs through, fits the model, extracts the information I need, coefficients, fit statistics, whatever, and then discards the model. And that should be good, right? So I created a model or a function. I called it fit mods because it fits my models, and I'm just that creative. And it does many things, right? But two of the main things that you'll see are important is it dynamically created the formula, right? Because I have these 120 different relationships to look at, 10 values, 12 different demographic predictors. So it dynamically creates the formula, fits the model, and then because multi-level models, especially fit to imputed data, tend to be they can be unruly beasts, as it were, right? They don't always converge. I had a little function that would take in the model, see if it had converged, and if it hadn't, apply some sort of like generic band-aids to see if we could get it to converge. And I thought, this is awesome, this should work great. It didn't work great. What ended up happening is I still was just running out of memory. It was taking way more memory than I thought it should. Fortunately, at the time, I was reading Hadley Wickham's book Advanced R, which is a lot of fun, right? Which apparently he ended up writing because he just wanted to know how R worked, and so he just spent a bunch of time like dinking around and figuring it out. And then he's like, "Hey, I learned a lot of stuff. Let's write a book." So I wrote this book, and I'd been reading it, and so I went in there and had some stuff about memory, and I realized that I had been making two mistakes without knowing it, two things that I probably never would have paid attention to if I hadn't had this particular type of data problem. And these are like two, I don't know, idiosyncrasies of the way that R handles memory. Number one, and this will seem significant as we look at our diagram here. Number one, if you create a formula in R, like an actual formula object, one of the things that it does is it captures what's called the enclosing environment. So essentially all the objects surrounding the formula that you create. It also does the same thing if you create a function inside of another function. It will capture the enclosing environment, all those objects around it. Now, the reason it does this is because in a formula and in a function, you're going to be calling and asking R to do things. It wants to make sure that you're not going to be asking it to do things with objects that it doesn't have any access to. So as sort of a precautionary measure, it takes everything that it thinks it's going to need and carries it with it. Now, what that means for me as a researcher is I ended up with a bunch of junk that I didn't actually need. And so here's what, again, I don't know the exact specifics, but here's basically what I think this meant for my project. So I have my fit mods function. I feed it my European Social Survey data. Let's say it's about 20 megabytes. I'm not exactly sure what it was, but say somewhere around there. Now, this fit mods function will very kindly go fit my 32,000 multi-level models. First thing it needs to do, though, is create a formula. So it's going to, again, do this process iteratively, right? So it's going to create lots and lots of formulas and lots of other things. So on one round through this, it creates a formula. Now that formula, because of the way R handles memory, it wants to make sure it has access to the things that the formula is making reference to. So it captures the enclosing environment. In this case, the function fit mods. So since these data have been pulled into this function, they get captured with this formula and carried along with the formula. So now this formula, which if you print out, it just looks like a little text string, is actually taking up 20 megabytes of memory, or 20 megabytes plus however many bytes it takes to actually store the rest of what it is. So then this formula then gets fed to the modeling function, and by default, the modeling function stores a copy of the data. I actually looked, I couldn't find a simple way of turning that off. And that again stores this 20 megabytes of data, but I was planning on getting rid of that. Like I was aware that this was a problem. Then I feed this model right, into my function, which again had been defined within this other function. So it captures the environment. What's in the environment? Well, the data are in the environment. I think by this point, the formula is in the environment. So that gets captured. And possibly, though I'm not sure about this, this model object might have been captured as well. So this little function, which was meant to just pull something in, tweak it if necessary, and spit it back out, as now adding megabytes of data. And again, this process is repeated thousands of times. And so I'm running out of memory again. So even if I go through and eliminate the model, which I did, I would still have all of this, essentially this junking up my system. So what did I do? Once I figured this out, hey, nice, some people knew that. That's awesome. Once I figured this out, the solution was actually pretty straightforward. Get a function that makes your formula, take that function, pull them outside of my fitmods function, which again, I originally didn't like to do because I like things to be all packaged nicely, right? I don't like a bunch of loose floating objects, but in R that didn't work very well, right? Once I did this, my final object, right, that had results from all 31,200 multi-level models took up a grand total of 245 megabytes. Right? That is significantly better than 780 gigabytes, right? And in this case, it was the difference between being able to run my models and not. So that was the first challenge that I ran into, right? And what I learned from doing this. Incidentally, if any of you are interested in parallel processing, I had quite an adventure trying to figure that out in R, and I failed, right? So if you want to have like a after the discussion chat about that, I would be really interested to hear some of your experiences with that. Okay, so that was the first challenge. Here is the second challenge. At this point, there is an enormous amount of information, right? I have 120 of these unique relationships, 10 values by 12 demographics. This is replicated in 8 different data sets. There's lots of information just going on here. And so I had to sit down and say, how do I go about presenting this in a way that is interpretable to somebody, right? And this was particularly important because the very first place that I tried to send this had a tight limit on the number of figures or tables that I could submit. So I was really trying to pack as much as I could into any given figure. And this made me think about like sort of 2 potentially competing principles: data density, or how much information can I stuff into one figure, versus data clarity, right? How understandable will my figure be to other people? And I don't think these things are necessarily always in conflict, but they often are. And so I had to think about, how am I going to do this? And this is actually the place where I'm guessing this will be sort of a topic for discussion, right, as we go through. So what I'm going to do, I'm going to show you what I decided to do. And I'd like you to think and say, is it good? Is it bad? What do we miss, right? And think about alternative ways potentially of doing this. Not only as a fun exercise, but then of course, if you come up with something awesome, I mean, that helps me too, right? So this is sort of a, hopefully we all win from this situation. But let me show you what I came up with. The first thing that I did is I decided, what is my core question, right? My core question is, do effects vary across these national contexts? So I said, how can I present that information in a way that's as compelling as possible? And so with all of that stuff that's been going on, what I came up with was this. So inside each of these cells is the proportion of those 120 effects that my test judged as being either a varying, like favoring a varying effects approach, non-varying effects, or cases where it wasn't clear, right? So varying effects means my random slope model fit better. I have evidence that the effect of, say, being an ethnic minority on conformity differs across countries. If my model that didn't have a random slope fit better, based again on that BIC criteria, then I would say the non-varying effects fit better, right? We have evidence that this effect is the same across different countries, right? Or at least we don't have evidence that it differs. And then in a number of cases, it was unclear, right? The BIC values were just really close to each other, so I couldn't make a judgment call. Now, my thought, right, as I go through this, is I say, I think that there are potentially some pros and some cons to presenting things like this. For instance, the crux of the research question can be answered with a single column, right? We want to know, do these effects vary across countries? And that number is a lot bigger than the other numbers, suggesting that yes, that is the case. Now, if we can answer this with essentially 3 numbers, did we need to figure it all, right? Could we just put this in the text? Now, I like the figure, obviously, because I like things that are visual. All of the rest of this is essentially giving the same information in replication, right? So this is simply saying, does it replicate? Now, visually, one of the things that I like about this is it gives you just a very clear sense, right? The color coding, for instance, again, the con here is that it's actually redundant information, right? It's not telling us anything that these numbers don't tell us. However, it is making it much easier to get a quick feel for what's going on in the data, right? It's in a way that that doesn't work with actual text numbers. You can look at this and immediately see, hey, that top row is a lot bluer than everywhere else, right? And so it gives you a feel for the data, which I like. But then the trade-off is I can't use color, for instance, to convey some other sort of information that might be useful. So potential pros and cons. One of them, I should mention as well, is that though I'm calling this a figure, this is actually a glorified table. It's a table with color, right? And it's actually a much simpler table than many of the tables we often put in into our work. Now, so this was the first figure that I came up with. I'm going to show you one more, and then we can break into groups. One of the things that this does really well, I think, is it emphasizes the replication of the pattern, right? That's one of the intentions. I wanted to say, hey, this finding is robust. You see it across all 8 of our samples. Now, what it doesn't do is answer many of the questions that I think readers might have. For instance, we're looking at 120 different combinations of demographic predictors predicting values. And then we're replicating that 8 times, right? People might say, well, that's great overall, but I kind of care about which of these relationships are replicating. Like, where are we seeing variation across nations and where are we not? So what I did is I took essentially this same information and I flipped it around. So now what I'm showing, what I'm highlighting are the 120 effects, right? So we have our 12 social locations, our demographic variables over here. Down along the bottom or in the columns, we have our different value types, and the numbers inside now represent how many of my 8 samples preferred the varying effects model. So in how many of my 8 samples, how many of my replications favored a model that said, hey, this effect varies across. So for instance, the relationship between being an ethnic minority and valuing conformity varied in all 8 of my samples, right? So the evidence is very strong that it matters, right? That whether, like, if you're an ethnic minority and we want to know how that relates to conformity, it matters whether you're in Germany or England or any of these other places. The effect varies across context, and it varies in all 8 of my samples, right? So that's a proportion of 1. Whereas the effect of being an ethnic minority on benevolence showed up in 88%. So I think that's 7 out of 8, right? 7 out of 8 of my replications. So what this allows you to do is to sort of assess the evidence for variation for every single individual effect that was tested, right? So up here, the evidence is actually not that strong. In only a quarter of samples, 2 out of 8, did we see that the varying effect model fit better for this specific relationship, right? Being separated versus separated, widowed, divorced versus not married, and conformity. Now, again, this table in many respects is like the last table in that is presenting proportions. It's sort of flipped around the information that you're seeing, right? So now it's emphasizing what's happening for each of these 120 relationships. And the replication isn't as visible in the table, right? So it's highlighting some information and hiding others. But again, it's a glorified table. It's using redundant color, right? The darker the blue, the higher the proportion. And potentially, so that's either a good thing or a bad thing, right? It's highlighting a pattern in a sort of a more visual, perhaps visceral way, good visceral, I hope, right? But then on the other hand, you can't use that color for anything else. But then you might say, given the fact that we want our plots to be clear, would we want to use color for something else? So those are the two of the figures that I came up with, right, to try and present this. Now, there are some things that are being presented here in a pretty straightforward manner. There are other things that are being hidden. One of the things, for instance, that is completely in the background is the fact that this whole proportion judging whether or not a particular relationship does or does not vary across national context, it all depends on this decision rule that I made, this cutoff that I said a difference of 2 in BIC values represents something real. And some people might be skeptical. They'd say, well, what happens? Like, how do your results change if you use a BIC difference of 4 or 6 or 10? And again, I would be deeply offended. I'd say, go read the rules of thumb, right, in the literature. But somebody brought this up, right? And so this is something that I have to think about. How do I do that? Is that information I could incorporate into the same figure in a way that wouldn't make it horrible to read? Or is that something that has to be somewhere else? How exactly do you display that? Because there's a lot of information. And then you're saying, let's vary it further, right? Let's add another, potential, you can imagine, for instance, a version of this that says, now this is sensitivity analysis 1, another plot, sensitivity analysis 2, another plot, right? And so is that the best way to do it? And so on. So what I'd like you to do now that I've sort of laid this all out here, is I'm going to do two things. I'm going to drop a copy of the relevant slides into the chat as soon as I find Zoom again, so that you can take them to your breakout rooms. And then when you go into your breakout rooms, let's see, we still have time, right? Yeah, we have time to go to breakout rooms for 7 or 8 minutes. Then, obviously talk about whatever you want. But if you want to talk about what's going on here, you might discuss questions like, what did we lose or what did we gain by displaying for instance, the choices that I made in terms of displaying results? Are there things that I was talking about the project, you said, that's really interesting, that's just missing, right? Should that be presented? Could it be added? Does it need to be in a separate figure? Maybe think about this 2-unit BIC difference. How would we incorporate a sensitivity analysis, especially if we're in a situation where we need to be sparing with the number of figures that we put into the plot? So here are a couple of ideas. So maybe Rohan, while you get this ready, what I will do